Hello everyone. In this week's QTFMS seminar, we are happy to host Giovanni Galati from Free University of Brussels. He will be talking about confining strings in a gapless environment. Giovanni, you can take it away.
Okay, so thank you very much. And also thank you to give me the opportunity to speak at this very nice series of seminars. So today we talk about this paper that I'm doing in collaboration with Jeremias Aguilera Damia and Giovanni Rizzi, and hopefully it will appear in the archive soon. So let me start giving some brief introduction. So, okay, the broad context of this talk is to talk about confinement. And I think I don't have to convince you that confinement is probably one of the most interesting but still mysterious phenomena in quantum field theory. So let me just list some of the things that we know, or at least we believe about confinement. So first of all, classically, indeed, whenever we have some gauge theory, we say that this theory confines if, at least classically, we put two charged particles, then the potential between these two particles must grow linearly with the distance between them. And therefore it will cost a lot of energy to separate them far away, and therefore they will be binded together. So when we go to the quantum level, then the same statement can be rephrased in terms of some correlation functions. And in particular, the observable that we have to look at is the so-called Wilson line, which is an operator that is more or less universal in any gauge theory, and is just, let's say, a gauge invariant way to express the integral of the gauge connection A. And in a confined theory, the expectation value of this Wilson loop must decays following this area law behavior. So this means that whenever we take this Wilson loop and we take it to be very, very large, then in a confined phase, we expect to have this exponential decay, which is controlled by the area of the loop and a dimensionful parameter, which is what we call tension. And notice that this tension is exactly the same coefficient that appears in the classical potential. Okay, so this is a way to characterize confinement in a quantum theory. However, let's say more recently, or at least starting from some years ago, we have now a more refined definition of what we mean by confinement, at least in a way which resemble the Landau paradigm to classifying IR phases. So what is the Landau classification? Is just characterizing a phase in terms of the realization of the symmetries in the vacuum. And what we understood is that in order to characterize what is confinement, we have to look at some generalized version of symmetry, which is a symmetry not acting on local operators, but instead acting on extended operators, and in this case, exactly on the Wilson lines defined before. These are the so-called one-form symmetries. And in this, using these one-form symmetries, one can define confinement in terms of as like the phase in which this one-form symmetry is unbroken. And therefore, connected to the previous definition, in this phase, all the order parameters must vanish. The value of the order parameters must vanish, and this is exactly the statement that the Wilson loop, which is charged under the one-form symmetry, must decay and goes to zero in the infrared. Okay, this is more or less how we define confinement and what are the established things. But of course, there are a lot of things that still we don't know and we would like to know better about confinement. For example, we don't have very precise understanding of what is the mechanism that trigger confinement. For example, in supersymmetric theories, where we have more handle on the non-perturbative physics, we know that sometimes confinement is triggered by monobole condensation. We also know that perhaps non-perturbative effects such as instantons and renormalons may be crucial for having confined phases. We also have a lot of more proposal for say the reason behind confinement, but still we don't have a universal understanding of what is going on during the, no, the strongly coupled uh, window of energies. Another thing that we would like to understand better about confinement is the universal implications of confined phases. For example, we know that in standard gauge theories, we have this more or less expectation that the states of a confined theories must be colored singlet, meaning that we cannot measure the gauge charge at infinity. Also, we know or we believe that in confined gauge theories, the actual states are bound states of electrically charged or quarks or charged particles, and also that these bound states follow some trajectories that we call Regge trajectories. And finally, another very interesting fact that we would like to understand better is the physics of flux tubes, which are just states created by the Wilson lines, which are confining. So they are objects inside the confined theory which are extended and they are created by Wilson lines. And let's say the presence of this flux tube is intimately connected to these Regge trajectories of hadrons and mesons. And as you may expect from the title of my talk, the focus of today will be on this last point, and in particular, I would like to say study a little bit more the physics of these flux tubes in confined theories. Okay, so this is more or less a very broad introduction. So let me now give some more detail on the things that we already know, or on the techniques that we already use in order to study these flux tubes. So first of all, what is usually happening in a confined phase, for example, in a standard Young-Mills theory, is that confinement is usually accompanied by a dynamical generation of a mass gap, which is of the order of the strong Kaplan scale. For example, Young-Mills, this is lambda QCD. And in these theories, the flux tubes usually carry a tension. Okay, this is the tension controlling also the area law behavior of the Wilson loop. And since the only scale of the problem is the mass gap, is this strong Kaplan scale, the tension of the flux tube must be of the order of this strong Kaplan scale. And since below this mass gap, the theory is completely trivial, is gapped with just a trivially gapped vacuum, we expect that if we consider a very long Wilson line creating this flux tube, then there should be a universal physics um, describing this very long flux tube. Just this because in this situation we cannot dynamically produce any particle in the bulk because we have um, not too much energy in order to produce a single state. And therefore, it is just a Wilson line embedded in a trivial theory. And this universality that I'm referring to is what people call effective string theory. And what is effective string theory? So according to the standard law of like any effective field theory, this effective string theory is just a universal way to describe some physics following the symmetry breaking pattern that we have in the infrared. And what is the symmetry breaking pattern governing the physics of these flux tubes? This is just the fact that whenever we have a flux tube in a trivial theory, we are automatically breaking the Poincare symmetry down to this subgroup. So we have in the bulk the d-dimensional Poincare symmetry, but because we are embedding a two-dimensional object inside this theory, this will break this Poincare to the two-dimensional Poincare preserved by the worldsheet and the transverse rotations. And therefore, the effective string theory is just the let's say the universal theory describing this symmetry breaking pattern. Okay, other questions about this?
Yeah, I have a question. Well, also,
Yeah.
uh, this condition about the isometry groups describe a condition about the topology of the manifold.
You mean this one?
Uh-huh.
Yeah, okay. I'm assuming to be on non-compact space. Like think about R4, and I put a string on R4 in a two-dimensional submanifold. And I'm assuming that the string is rotationally symmetric so that it doesn't break this isometry. Of course, one can consider also more complicated strings which breaks this rotational symmetry, and you just need to change this part. So this is somewhat universal. It's just the Poincare symmetry of the worksheet. This is more special in the sense that it requires some extra assumption.
Okay, thanks.
Okay.
Yeah,
Okay,
I
so
also do have a question.
yeah,
The right-hand side is the subgroup of the left-hand side, right? You said.
yeah.
Okay, so are they connected by a spectral sequence?
Uh, yeah, sure.
So
Well,
they
I don't know if it splits.
Mhm.
Uh, no, I think no. But
I
okay,
see.
I'm not sure, and it will not be important.
Okay, I see.
Okay. Okay, so we can also be more quantitative on this effective string theory, and indeed we can write an action. This is just as we as we usually do for standard effective field theories and nonlinear sigma models. We also have an action for this effective string theory in terms of some Goldstone bosons. And this is the very famous Nambu-Goto action, which describes a string embedded in a trivial bulk. And okay, the number of Goldstone bosons is d minus 2, where d is the space-time dimension. And why d minus 2 is just this describes the fluctuation of the string in the transverse direction. Indeed, it's very well known that whenever we have this symmetry breaking pattern for space-time symmetries, the number of Goldstone boson is not the standard counting that we do for internal symmetry. What we usually get is less number of Goldstone boson, in this case is d minus 2. And these are these x here. And okay, now that we have a Lagrangian or an action for this theory, we can now use it to generate predictions. For example, there are standard quantities that one can compute in this theory. One of them is the energy levels of a closed string. So we take our worksheet and we put it on a closed circle times r in the time direction, and then we can let's say compute the spectrum and compute the energy levels of the spectrum. And for example, the ground state will have this generic form. So you will have a piece which is growing linearly with the radius, and this is the analog of the classical confining potential. So if you see this growing linearly with L, and it has like the proportionality constant, which is the tension. And then it will have a term which decays with L. And this is just the coming from the contribution of these fluctuating Goldstone bosons. And this is usually called the Lusher term. So you see that it decays as 1 over L, and it has this proportionality factor, which is counting the number of Goldstone bosons. And then there are universal subleading effects, which will not be important for this talk.
Sorry, I have another question.
Yeah.
For all these calculations, you are using a canonical quantization, or you are using, I have read that sometimes using BRST quantization and some Gauss fields for string theory, but I am not sure.
No, in this case, you can do it either with standard canonical quantization. You can also do it with doing a path integral. So you see, if I truncate up to this term, this is just a quadratic action. I can also do the path integral and compute the ground state energy.
Okay,
The exact path integral is
so
you don't need
canonical.
yeah, the Gauss. Okay.
Thanks.
Okay. Okay, so this is one of the observable one can compute. There is another one that I would like to mention, which is the width. So as I said, this is like a two-dimensional object embedded in d dimensions. But now these fields x, which correspond to the transverse fluctuation, are dynamical. And therefore, even if we start with a two-dimensional object, this will acquire a little width in the transverse direction because of this fluctuation. And we can compute exactly what is this width. So of course, here there is a twiddle because we can compute this width using different observables. We just need to find an observable which is sensitive to this fluctuation. But okay, the generic behavior of this width will be that it decays as 1 over t, where t is the tension, and it is proportional to this logarithmic, to this log of L. And as you know, like if you know something about the two-dimensional compact bosons, which is the theory describing this sigma model, you know that this is very connected to the propagator of two-dimensional compact bosons, which has this log behavior. So what you see is that there is an enhancement of the width coming from this very huge fluctuation of the compact boson in two dimensions. Okay, so this is the standard thing about effective string theory. But now I would like to describe a situation which goes a little bit beyond the assumption I mentioned. So if you remember, the starting point I said is that usually in confined theories, we have a strong Kabul scale, which also set the mass gap. But this is not quite true in all the situation. Indeed, there can be cases in which our theory is confining, is strongly coupled, and we have a strong coupling scale lambda, but still the mass gap is parametrically small with respect to this strong coupling scale. For example, there is a very recent study by this group of people, which is also is a very it was an inspiration for our work, where these people studied the case of quantum electrodynamics in three dimensions with Polyakov confinement. So in this case, indeed, quantum electrodynamics in three dimensions is strongly coupled, and the strong Clavis scale is set by the electric charge, which in three dimensions is dimensionful, so it's set a scale. But then there is a mass gap which is not of the same order of E, but is set by the non-perturbative generation of a mass gap due to monopole proliferation. And this is the mechanism which was discovered by Polyakov a long time ago. So we have two scales. One is the strong Clavis scale lambda, and one is M, and the two are parametrically different. And what these people realized is that in this situation, we still have confining strings and the corresponding flux tubes. But the effective string theory can be recovered only if we consider loops which are bigger than the mass gap M. So for energies which are below M. But then there is still an effective field theory description of these flux tubes in the energies between lambda and m. It's just that in this range of energies, the theory is not genuinely two-dimensional, so we cannot write an Nabucco action of this form with a two-dimensional Wordsheet action. We will have a genuine four-dimensional theory where we can describe the flux tubes and the corresponding bulk massive states, and we can also describe the interaction between them. Okay, so this is one way to go beyond the effective string theory, but what I want to stress in this talk is that there is a more drastic situation that can happen, and the situation is the case in which we have a theory which is confining, but still it is gapless, so there is no mass gap. There are massless degrees of freedom in the bulk, but still we have confining strings, Wilson lines which have an area law, and the corresponding dynamical flux tubes. And notice also that this situation is very close to actual QCD, in which we have let's say pions, which, okay, in the real world are massive, but they are almost massless. They are pseudo Wilson bosons. And we expect confinement to still hold in the massless case. We still expect that QCD confines with some caveats, but okay, just to make contact with the QCD. But generically, what we expected is that in this situation, we will have a genuine effective field, four-dimensional effective field theory, which will describe the interaction between flux tubes and massless pions. And there is no limit of energies in which the 2D Nabucco description is available. Okay, so as I said, the goal of this talk is to describe this situation. And in particular, I would like to find a case in which this physics is tractable in the sense that is weakly coupled, and therefore we can make genuine prediction about it, about this. And as I'm going to describe in the few next slides, the example that fits this requirement is the four-dimensional CP1 nonlinear sigma model, which is just the sigma model describing the symmetry breaking pattern of an SU2 flavored symmetry down to its U1 subgroup. And also I want to stress that this example is not only a nice example because it is a tractable toy model for this situation, is also relevant for more interesting theories like QCD, a joint QCD with a SU2 gauge symmetry. Okay, other question about the motivations? Okay, so let me go to describe in more detail this model. Okay, so the CP1 is isomorphic to a two-dimensional sphere, and therefore we can write the action in different ways. This maybe is the more standard way where we parameterize the sphere, embedding it in R3, and then using the three-dimensional coordinates with this constraint. However, there is a more useful presentation in terms of the stereographic coordinates of the sphere, where we use this variable omega, which is a complex scalar. And why this is more useful is because while in this action we have to implement this constraint by hand in the path integral, in these variables omega is completely unconstrained, and therefore the path integral is more easy to do since we don't have to implement any constraint. What you see is that in the presentation, however, there are infinitely many interactions between all these omega just coming from the metric of the sigma model. And also an important piece of this action is this coupling constant G, which is dimensionful and indeed it sets the strong coupling scale. Or from the effective field theory point of view, it just set the UV cutoff above which we cannot use the effective field theory description anymore. Okay, so what are the symmetries of this model? Of course, there is a O3 zero form global symmetry, which is the one which is the symmetry of the sphere. So there is the SU2 part, which acts on omega like this. And you see that there is a U1 subgroup, the one where we set B to 0, which is acting linearly on omega, and therefore this is the preserved subgroup of SU2 of the model. And then there is the discrete Z2, which is just like the reflection of omega. So these are the standard symmetries of the action, but importantly, there are also more sophisticated symmetry, in particular the one from symmetry I was referring in the introduction. And what is this one from symmetry in this case is just the statement that the theory possesses a two-form current J, namely has two indices, J mu nu, which is constructed in this way. And just from by construction, one can verify that this current is conserved. So you don't need to implement any equations of motion. This current is conserved also of shell, and this is what we usually call topological symmetry. And if one want to be fancier, this symmetry just comes from the topology of the sphere. In particular, comes from the fact that the second homotopy group of the sphere is non-trivial. But okay, it is not relevant. So the important point is that one can construct a current which is conserved automatically. And since we have a one-form symmetry, we can also discuss about line operators, which are charged under this symmetry, and we can ask about confinement. Okay, so the last ingredient that I want to mention about this theory is that this is weakly coupled in the infrared, namely is IR free. And this implies that if we want to discuss about infrared physics, classical considerations are not so bad. So something that we can see classically will not be spoiled at the quantum level, will just be slightly deformed. And indeed, one can see in these theories, this was known long time ago, that this theory possesses solutions of the equations of motion, which have a non-trivial one-form symmetry charge and also have a finite tension. So what I'm saying is that there is a configuration of omega which depends only on two coordinates, which if you think about flux tubes, these coordinates will parameterize the transverse direction of this string. And this omega is such that it solves the equations of motion. If we evaluate the one-form symmetry charge of this solution is a non-zero integer. And also, if we compute the on-shell action, we will get, of course, the terms coming from the volume of the worksheet, but then we will get a tension, which is a finite number. Therefore, what we conclude that line operators generated in this configuration have an area law. This comes from this on-shell action. And the theory, therefore, is confined and it has dynamical flux tubes. Okay, we can be also more specific on these solutions. Indeed, if we write the equations of motion, this as this form. But okay, if we assume that our classical solution only depends on two of the four out of the four coordinates, then we can do a trick. We can do a change of variable from x1, x2 to a complex coordinates z. And what we get is that the equations of motion drastically simplified. It just becomes holomorphic and anti-holomorphic equations. And therefore, a solution of these equations of motion is just an holomorphic function, like omega, which depends only on z and not on z bar. And also, if we demand that this solution has a non-trivial one-form symmetry charge, what we find is that the generic solution of this set of equation takes this form. So it is a fraction of two polynomials, p and q. These polynomials must have no common zeros. And one can check, let's say, by doing the computation that the one-form symmetry charge of this solution will be just the maximal degree between the two polynomials. So, for example, this is the generic form that we can write for a charge n string. So it will be the ratio of two polynomials. And in the numerator, we choose a polynomial of degree n minus 1. In the denominator, we choose a polynomial of degree n. And then this solution will be automatically a solution of the equations of motion, and it will have a one-form symmetry charge equal to n. And also, we can compute the on-shell action. Just take this solution, plug back into the action, and what we get is this tension. So we see that the tension grows linearly with the charge n, and it has this behavior 4 pi over g squared. Okay, are there questions? Okay.
Just a question about your terminology. By
Yeah.
Belevin-Polyakov instantons, you don't mean the self-dual instantons in Yang-Mills theory, right?
No, yeah,
You mean the two-dimensional CP instantons.
exactly. So
Okay.
Belevin polygon discussed the instantons in two-dimensional CP1 or CPN in general. And these solutions are just the uplift in four dimension where the instantons now becomes strings.
So there's no relation with the Yang-Mills self-dual instantons.
No,
Just to
no,
be
no,
clear.
no.
Okay, good.
This is way easier. You see, it's just a polynomial in Z, while the self-dual instantons, Young-Mills instantons are more complicated. This is why this theory also is more tractable. Okay, so let's now look more closer to this solution. As you see, there are these coefficients of the polynomial P1, Pn, and Q1, Qn, which do not enter in the tension. So you see that for whatever polynomial I choose, if I choose the polynomial such that there is no cancellation between the numerator and denominator, and the degree of the polynomial doesn't change, then this will be just a family of solution with the same tension. Not only the same tension, but also the same one-form symmetry charge. Therefore, the sets of Pi and Qi will define for me a moduli space of strings, at least a classical moduli space of string. With moduli space, I just mean, let's say, a family of solution with the same properties. And what is the physical interpretation of this moduli space? So let's take, for example, n equal to 1. So for n equal to 1, the solution takes this very simple form. So it is, let's say, a complex number divided by z minus z0, where z0 is another complex number. And therefore, you see that we have four moduli. There is z0, so the real part and the imaginary part of z0. Then there is lambda and alpha. So z0 is very easy to understand. It's just the position of the string. Of course, the string is a two-dimensional object embedded in R4. Therefore, we have to specify two out of the four coordinates. And of course, we expect that nothing will depend on this position. This will be a modulus of the solution. And this indeed corresponds to the symmetry breaking pattern of Poincaré. This Z0 will break Poincaré to this group which I wrote before. So what about lambda and alpha? So one can see that lambda defines the classical width of this configuration. So if you plot this configuration as a function of the transverse coordinate, you see that this is decaying, and the width of this decay is lambda. And alpha finally is just the fact that whenever we choose this solution, we will break the U1 global symmetry preserved by the bulk. And therefore, this is the modulus related to this U1 symmetry breaking. Indeed, this is an angle. So this was about n equal to 1. So what about n bigger than 1? Indeed, you see that there are many more moduli for n bigger than 1. And the interpretation of this number of moduli comes from this very important relation between tensions. Indeed, from this generic form of the string tension, what you see is that the tension of the charge n string is automatically n times the tension of the charge 1 string. What this is implying that if we put two strings of charge 1 at position z0 and one at position z1, for example, what is happening is that at least classically there is no classical force between them. One can change z0 and z1 independently, and there is no cost of energy in doing this translation. And therefore, this implies that implies the existence of these many more moduli, because what you see is that you can change the relative position between charge 1 string, and this will be a generic solution of the charge n string. And also you can change the relative size, the relative width of all these charge 1, and also the relative U1 phase. And if you do the proper counting, this accounts for all these moduli. Okay, so for the purposes of this talk, I will focus on the charge 1 string because it's way easier. Also, in the paper, we basically do all the calculations for the charge 1, and we only have some little comments about the higher charges. So, okay, let's now focus on this solution. Keep in mind this solution and these four moduli. Okay, so this was about the classical things of the strings. So
Can I
something
ask a
that,
question?
yeah, sure.
Sorry. If you go to the large charge sector, is there anything semi-classically interesting in that sector?
Yeah, so you can do some approximation, especially when we go to the quantum level. There are some things that are suppressed at large charge, but it's not something very, at least we didn't find something uh, which simplifies a lot. It is
Hmm.
just some relabeling of the calculation, but it's not something of it's not so powerful as the standard large charge
Hmm.
of the local operators, at least in this case.
Okay.
And we didn't explore this very further, so there can be
Okay.
something in there that I didn't see.
Okay, thanks.
Okay. So this was about the classical statements of this string. Let's now go to the quantum level. So how do we go to the quantum level? We just take this classical configuration and we just do fluctuations around it. This is actually what we do in standard quantum field theory, just that in the standard case, we expand around the trivial vacuum, which is the trivial solution of the equations of motion. In this case, we just expand around a non-trivial solution, and this will give us the semi-classical spectrum of this string. Okay, so we do this, we give these ansatz to our pions omega, and then we just plug these ansatz into the action, and we truncate that to the quadratic order in psi. This will give us like the semi-classical spectrum of the theory. And what we find is, of course, the classical piece, which is this 4 pi over g square coming from the classical configuration, and then we get a quadratic part, a quadratic term for psi, coming with a differential operator p. But of course, as you see, since we are expanding around the highly non-trivial solution, this this differential operator will not be just the kinetic term, but we will also have a non-trivial dependence on the classical configuration omega. Okay, so now we have to find the eigenfunctions of this operator P. This will give us the spectrum. And okay, since there is some symmetries involved in this problem, for example, for the charge one string, this one can see that this is invariant under the transverse rotation around the center Z0. And also you see that since this omega classical just depends on the transverse coordinate, all the dependence on the worldsheet coordinates will be just the standard free wave equation. So using these symmetries, one can produce an ansatz for the eigenfunctions. So you see that there is a plane wave, a free plane wave for the worldsheet coordinates, so which I call sigma. Then since we have rotational symmetry, we can expand the solution in the transverse direction in angular modes. And then the only non-trivial function that we have to determine is this psi m of r, where r now parameterizes only the radial distance from the string. So you see that we reduce our eigenfunction problem into just a problem for a single function psi. And what is the differential equation that we get for psi using this ansatz? So what we find is like a Schrödinger-like equation. So we find h psi equal to k square psi. So what are the variables involved into this equation? So we have a dimensionless radial coordinate u, which is just using this ratio r over lambda. So notice that lambda is dimensionful as a dimension of a length, and therefore r over lambda is just a dimensionless way to parameterize the distance from the string. Then we also have a dimensionless energy, k, using again the dimensionful parameter lambda in order to cook up a dimensionless combination of the eigenvalues. And then we have the Hamiltonian. So the Hamiltonian will be this differential operator, is a second order, And then we have a potential which depends on the radial coordinates and on the angular modes m. So this, as a first look, is a complicated differential equation, and indeed it remains complicated. However, what one can notice is that this H has a very nice property. Indeed, one can realize that this H can be written as A dagger A for a given operator A. In particular, this is the form of A. Is a first order differential operator, and one can see that this Hamiltonian factorize into a square of this operator. And if you know something about supersymmetric quantum mechanics, it is actually the definition of a supersymmetric quantum mechanics. What we see is that the the Schrödinger equation that we find for the radial modes of the spectrum is supersymmetric, at least classically. And what this is implying that the eigenvalues, namely the energies of the spectrum, must be positive, or no, let's say non-negative, can be zero or positive. And this is very important from the point of view of the string. What is implying? Is implying that since there is no negative bound state, namely a bound state with a negative energy, what this implies, implying that there is no tachyon which destabilizes the string, and therefore these strings are classically stable. They don't, there is no instability at the classical level. Okay, so this is the setup of the equations for the spectrum. So we already know that the spectrum is bounded from zero, and so it must have energies starting from zero or positive. So now we can look at the actual solutions of this spectrum. And let's start from the zero mode. So the zero modes are the solution of of this equation, which have zero energy, namely k equal to zero. And because of the factorization of H in terms of the differential operator A, the solution of the zero modes are way easier. Indeed, one can show that the solutions of H psi equal to zero are in one-to-one correspondence with this simpler solution, AXI equal to zero. So it's simpler because now A is a first order differential operator. And therefore, one can easily determine the solution of this equation, and you find this expression. It's just a very easy, let's say, function of u. And you can also compute the norm of these eigenfunctions. And what we find is that only the one with m equal to -2 is normalizable. Therefore, we find just one complex normalizable zero mode. And one can easily check that this zero mode corresponds to the modulus z0 of the solution. What I mean by corresponds, I mean that if I take my classical solution, which was lambda over z minus z0, and we give to z0 a dependence on the space-time direction, what you find is that, of course, since this is a modulus, the corresponding fluctuation of z0 will be automatically an eigenfunctions of the Hamiltonian with zero energy, because classically you don't pay an energy to change z0. Okay, so we have an interpretation of this normalizable zero mode in terms of z0, but what about lambda and alpha? So we have extra moduli in the classical solution, but we are not finding any corresponding zero mode. And the solution to this apparent puzzle comes from this very nice paper of Intrilicheto and Seiberg of more or less 10 years ago. What they show is that in this case, if you, for example, take the classical solution and do the same trick we did for z0, namely we take lambda and alpha and we give them a dependence on the spacetime. What you get is that it's true that this will give automatically an eigenfunction of the Hamiltonian with zero energy. However, the kinetic term for these zero modes will diverge as a log of r, where r is like the transverse direction. So suppose I take the transverse direction, I cut off it at a given length r, then what you see is that the kinetic term of these zero modes diverges as log of r in the infinite volume limit. So since we are doing the computation in the infinite volume limit, so for the transverse direction goes to infinity, what you're actually getting is that in order to get a finite action, the only solution is that this lambda and alpha must be constant, cannot depend on sigma, and therefore this action is automatically zero. Therefore, what this is saying is that lambda and alpha are frozen in the infinite volume limit, and okay, and therefore these lambda and alpha are not just dynamical fields, are parameters of the string, even at the quantum level. What I'm saying is that for any quantum string, so there is a quantum string for any lambda and alpha, so and then they are parameterizing a family of strings, even at the quantum level. And therefore, even if we fix one lambda and one alpha, there is no dynamical process which can change this value with a finite cost of energy. So are there questions about these zero modes?
Yes, I have
Yeah,
one question and one comment.
yeah,
What you say when you are talking about supersymmetry? I don't get it still. And the second
yeah.
one is this almost resembles to me to a quantum oscillator in some level, like a string theory quantum oscillator. I don't know. It's something to use. Means something to you?
Yeah, so when I say supersymmetry, it's just supersymmetric quantum mechanics, which is very broad. It's not. Uh, it's just the fact that whenever an Hamiltonian has this factorized form, you can write the Hamiltonian as an anticommutator of supercharges, but it's not very deep. It's just you can forget about the word supersymmetry and just say that when an Hamiltonian has this factorized form, of course, the eigenfunctions are way easier.
Mhm.
But okay, there is no deep supersymmetry behind this model. Also, this is just classic. It's just semi-classical. If you compute interactions, we don't truncate this expansion at the quadratic order. Of course, the supersymmetry will be lost. Okay, and the harmonic oscillator is another example, I think, of supersymmetric quantum mechanics. Also, the harmonic oscillator can be written as a dagger A for some differential operator. So probably this is why it resembles to you this.
Yeah, it's like quantum oscillator in string theory, something like that.
Yeah.
Like,
Okay. Okay, so this was the discussion about zero modes. But of course, we have to also look at the excited states, so the eigenfunctions of the differential operator P with positive energies. And unfortunately, in this case, the differential equation cannot be simplified, and we cannot find any analytical solution. However, it's very easy to solve this solution numerically, and also there are a lot of analytic prediction and approximation that one can do on this equation. For example, one can easily see that there is a solution for every energy above zero. So for any positive energy, there is a solution and a corresponding state. Therefore, we find a continuum of scattering states starting from zero. And this is somewhat expected, is because, of course, we know that in the bulk there are massless pions. And this continuum of states is just describing these massless pions and their interaction with the string. So, of course, the string can change the quantitative behavior of the pions, but it cannot change the fact that there are the pions. And this is just the statement that we are recovering the pions in the string sector. And, and of course, as I said, the presence of the string will change the quantitative behavior of these pions. Indeed, if we find the eigenfunctions of the differential operator, what we find is that they take this generic form. So, okay, these J and Y are the Bessel function, and that parameterize a generic solution of the scalar solution in two dimension. And the non-trivial dependence, the non-trivial, let's say, imprint of the string comes from this function A and delta. So if we set A and delta to be trivial, then we just find the wave function of the pions in a trivial background, so just free scalars. But since this A and delta depends on U and K, this is implying that the pions are perturbed by the string. And in particular, one very important quantity which characterizes this perturbation is the so-called phase shift, delta, of K, which is the limit of this delta in the when U is very big. So remember the U parameterize the transverse distance from the string. And therefore, what is the interpretation of this phase shift? So we are just preparing a pion at minus infinity. So we let him scatter through the string, and we just see how it changes when it comes back at infinity. So this delta is parameterizing this change when the pions scatter off the string. And of course, this delta cannot be computed analytically. However, there are a lot of beautiful analytical constraints that this phase shift must satisfy. And I refer you to the paper when it will appear for the details of these analytical approximations. However, for the purpose of this talk, we can just look at the numerical behavior of the phase shift. So you see that is increasing starting from 0 and it reaches pi. And one can also see that the fact that it reaches pi must be true due to the Levinson theorem. But okay, I will not enter into the detail of this, will not be very important. And why the phase shift is important is because one can show that using the phase shift we can recover the density of states of the string. Or in part, more precisely, we can compute the difference between the density of states of the string minus the density of states in the trivial background. And what one can show is that this difference is just proportional to the derivative of the phase shift. Therefore, if we have the phase shift, we have the density of states. So let me give a brief recap of what we found about the spectrum. So for a charge one string, what we found is a single complex zero mode, which is just coming from the position of the string. And then two frozen parameters, lambda and alpha, and also a continuum spectrum for any energy bigger than one and the relatively density of state. Okay, if there are no questions, I will go now to use these results to compute observables.
I have a question. So
Yeah.
when we have a soliton, let's say solution, and it has some moduli space, in the
Yes.
path integral, we integrate over the moduli variables, and sometimes we recover some broken symmetries since we are integrating over the moduli space. Do you have anything like this in this scenario where the parameters are frozen, for example, in lambda and alpha? Because I cannot see if that should be the case or not.
So no, because we are not integrating over lambda and alpha, so these will be still broken symmetries. Instead, for Z0, this just the fact that we are recovering Poincare is just non linearly realized on Z0. This is why it's
Hmm.
spontaneous breaking of Poincare. So this
So,
Z0 corresponds to the breaking of Poincare, but since now we are letting Z0 to be fluctuating, then Poincare will act on Z0, but the action is invariant, it's just non
hmm,
linearly realized.
hmm,
Yeah, while lambda and alpha, for example, alpha is a U1 symmetry, and we are choosing a value of U1 at infinity. We are choosing a value.
hmm. Okay, so we're not doing like a moduli space integral over these two
Yeah, no,
frozen
because this
parameters.
will be infinite. Yeah.
Okay, so if we change those parameters, they will give different strings.
Yeah.
Okay,
But the point is that there is no dynamic. Once you choose a parameter, there is no dynamical process which will change this parameter. So if you want, it's a
okay,
super selection sector.
okay. Now it's more clear. Thanks.
Okay. So since I have very few minutes, I think, how many minutes do you have?
You can keep going as long as you want.
Okay. So let's go to the computation of the observables. The first one is the one loop string tension. So you see, if you remember, before I computed the classical string tension, and it was 4 pi over g square for the charge one string. But now we can compute also fluctuations. And how we can compute fluctuations is just doing explicitly the path integral over the fluctuation psi. This will give a correction to the string tension, which will be, say, a one loop computation. And since we know now the spectrum of the operator P, we can just compute the one loop determinant in an easy way. So you know that whenever we do the path integral over the fluctuation psi, this will produce a trace of the log of the determinant of P. But now, since we have the entire spectrum of P, the trace of the determinant will be very easy. It's just the determinant will be just the sum, or since these are continuum of states, it will be an integral of all the eigenvalues of the eigenfunctions. So this will have a first part. So let me be more specific. This will have a first part, which is the zero mode. So the zero mode has eigenvalue Q because has transverse energy zero. So remember that the energy is Q square plus K square, but K square is equal to zero. So the zero mode has Q equal only Q square. Then you take the log and you do the trace. The trace is the integral. So this is the zero mode. And then you have the excited states. The excited states depends on all the coordinates. So they have eigenvalue Q square plus K square. Then you do the log. But then, of course, since you have a continuum spectrum, you have to weight this log with the density of states, and then you do the trace. So you integrate over Q and K. And this will be our one loop computation. So before doing the actual integrals, let me do some remarks. The first one is that the string tension, as it is not scheme independent. And this you can understand it already from the classical part because it is 4 pi over g square, but g is a relevant coupling. So you can just change your definition of g using a counter term, and this will change t. So t is subject to some scheme independent part. And for example, a scheme independent quantity which one can compute out of the string is a difference between strings, tension of strings. For example, one can take the charge and string, the charge one string, and compute this quantity. This will measure the stability of the charge and string. And this one can show that this combination is scheme independent. So, however, as I said, we will focus on just the T1 part, but keep in mind that this is just a part of the computation in order to make some actual observable. And the second remark is that since we are doing a one-loop computation of our two derivative action, according to the standard effective field theory principles, we need to also include the four derivative terms at tree level. And for the CP1 or linear sigma model, the four derivative terms are these two. But since we must do the tree-level computation for this. We just need, what does it mean for the ground state energy? This means that we have to evaluate them in the classical configuration. And what one can see is that the second one just vanish in the classical configuration, while the second one it gives a number, just a combination of lambda and the four derivative coupling y. And also remember that y has its own renormalization, beta function and renormalization. Okay, so this is the four derivative contribution. And now we can do our computation of the string tension. So it will have the one loop contribution and the four derivative classical contribution. And of course, as I said, this quantity scheme dependent, and therefore we have to choose a scheme. First of all, we have to choose a regularization because these integrals are UV divergent as standard in computation of quantum field theory. And we use the dimensional regularization and the MS bar scheme. And what we found is this. Sorry, is this. So let me unpack this equation. So we have the 4 pi over g square, which is the classical part, is the first term. Then we have a lot of terms which are all proportional to g square times lambda square. So you see that the actual expansion that we are doing, so of course, an expansion in perturbation theory must be an expansion in terms of a dimensionless coupling. And the dimensionless coupling in this context is g square over lambda square. Remember that lambda is dimensionful, and therefore g square over lambda square is one can check that is dimensionless. And what this is implying that the actual perturbation theory is valid only if lambda square is way bigger than g square. This is implying that not all the strings are inside our perturbation theory, just the one with lambda square bigger than g. Okay. And then, okay, there are these alpha and beta. The alpha and beta are just pure numbers, just pure numbers that one can compute numerically. They depend on the phase shift. So the entire dependence on the phase shift is in these two numbers, alpha and beta. And then there are these other two quantities that comes from the renormalization of the quartic coupling y. And you will produce a divergent term in 1 over epsilon, and then a renormalized coupling y. So what you see is that this tension has two divergent terms, but since of course we want a finite tension, what must happening is that these two terms must cancel. And this will produce a highly non-trivial constraint on this number beta, which is a function of delta. So remember, delta is produced doing solving the eigenvalue problem of a differential operator. And now we are connecting this number to a completely different number, which comes from the beta function of the quartic coupling. And indeed, one can verify numerically and also analytically using the analytical properties of the phase shift that indeed is true. Beta is equal to 1 over 9 pi, and therefore the tension is completely finite. Okay, so this was about the tension. Now what we can do is actually also compute the ground state energy of a closed string. This, remember, is one of the observables of the effective string theory. And so in order to remove the linear part, the one that grows as the tension, which is something that we already computed, what we can do in order to just isolate the finite L contributions is to take this combination. So you take the ground state energy as a function of L, which is now we are taking the string to be in a circle, on a circle, and then we subtract is infinite L limit. And what one can show is that this combination is exactly scheme independent and therefore is a more proper observable of the charge one string. And we can compute this observable using very similar techniques on the one I described before for the tension. And what we find is this. So this delta t. So we find that, okay, it decays as 1 over L square. Then you have a constant p is 1, which comes from the zero modes contribution. And then there is a non-trivial function of lambda over L, which I can write it explicitly, is just, let's say, again, an integral of the phase shift weighted with some complicated function. This is just a determined function of x, of lambda over L. And of course, okay, this must be done numerically because the phase shift, we know the phase shift only numerically, but we can also compute its asymptotics using the analytics we know about the phase shift. So let me just plot it, the final answer. So this is what we get. We get the finite L contribution to the ground state energy is a growing negative and growing function, and it asymptotes to some negative value. So let me now describe what this function is. So okay, before just let me put all the ingredients together. So the ground state energy now has the linear part, which is the one we computed before for the tension. So is L times T. and this is the tension at one loop. And then this is the part we just computed now, the 1 over L contribution. And you see that this resembles a lot the effective string theory result is L times T times pi over 3L times a function. So for effective string theory, the function was 1. In this case, it's just a non-trivial function of lambda over L. And let me just emphasize that the validity of this computation is just for lambda bigger than G, because this is the one loop computation of the string tension, and L much bigger than G, because we have to consider very big loops in order to be in the infrared. And indeed, what we notice is that if we take extremely big loops, so L way bigger than lambda, not only bigger than G, but also bigger than lambda, what we get is that the ground state energy approaches the effective string theory ground state energy. This is because this J goes to 0, and therefore we just get the effective string theory. And why this is happening? So this is happening because if we take L to be the bigger scale in the problem, we are just probing the far infrared fixed point of the theory. But what is the infrared fixed point of the theory? It's just the theory of free scalars, because any nonlinear sigma model in the far infrared is just a theory of free scalars. But of course, we know that in a theory of free scalars, there is no confinement and no dynamical string. And therefore, in this limit, the dynamics of the string decouples from the bulk. Therefore, the bulk is not anymore affecting the dynamics of the string, which becomes just a string embedded in a trivial bulk, and therefore it will produce the standard effective string theory predictions. Okay, other questions about this computation? Okay. So we also computed the string width, which was one of the other observable I mentioned in the introduction. For example, okay, as I said in the introduction, the actual width must be defined using some observable which is probing the width of the string. For example, a very often used observable is the expectation value of the electric field parallel to the string, and in particular its behavior when we look at the transverse direction. Indeed, in a confined theory, we know that the electric field must decay because it cannot have long range interactions. And therefore, we have a decaying function and we can compute its width, for example, using the first absolute moment of the distribution. Okay, so this is a particular way to define a width. And what is the electric field in the CP1 nonlinear sigma model? It's just one can construct an electric field just using the one from symmetric current. Indeed, we know that whenever we have a one from symmetric current, we can just take its time component, and this will define for us an electric field. And in particular, if we use the classical configuration of the charge one string, this is the electric field we get. And okay, so now we can compute explicitly this width. So first of all, this is the effective string theory prediction using this explicit definition. And you see that it has the qualitative behavior I mentioned in the beginning. It has a log behavior, and it decays as a tension. But now we also have the correct prefactor, square root of pi over 2. And now we can also compute the width in our CP1 nonlinear sigma model. Okay, this will be a complicated function. It's not important. But the important thing is that it will depend on two parameters. One is this L, these are defined here, and one is this alpha, which will take into account also the parameter lambda. So you know that as you may notice in the effective string theory there is no lambda, while in our explicit model there is also an extra parameter, and the width we computed will also depend on this one, in particular in this particular combination. And this is the plot of the width we get. So it's an increasing function of alpha that takes this form. But now let's unpack what is the behavior of this width. So for small alpha, what we are getting is that we are recovering the effective string theory. And this is in line with the comment I already made in the ground state energy. Indeed, when alpha is going to 0, this means that L must be very, very big. And in this case, still the bulk decouples, and we must get the effective string theory with the correct prefactors. But also, if we take the alpha going to infinity limit, what we are getting is the classical width, namely the lambda. What I said before is that lambda is controlling the width of the classical configuration. Indeed, what we are seeing is that in the alpha going to infinity limit, the fluctuation of the zero modes are completely negligible, and the width will approach its classical value. And in the range between 0 and infinity, this will be an interpolating function between the effective string theory and the classical prediction. This blue line here. Okay, so this was the two observables I wanted to comment. So if you have questions, this is the time, otherwise we'll go to the conclusion. Okay. So let me just make some conclusion. Okay, so as what we discussed are confining strings of the CP1 linear sigma model. And we also emphasize the contribution coming from the massless pions, which are in sharp contrast with the classical assumption on effective string theory. And what we have seen is that crucially, some of the classical zero modes do not become dynamical and becomes actual parameters of the string. And what we have seen is that the observables crucially depends on this parameter, and they approach different predictions depending on the different values of this parameter. Of course, this is an effective field theory statement. When we go to some UV completions, these parameters will not be zero modes, will not be moduli of the solution, and therefore what will happen in some UV completion is that different UV completions will select different values of this parameter. Therefore, all the plot that I showed to you, you must select one of the points in these plots whenever we have some UV completion that flows to the CP1 or linear sigma model. For example, this will be the case of the SU2 adjoint QCD, or at least this is what we believe based on this paper. But we also have comment about higher NC, and unfortunately, these are more pessimistic in the sense that we have some arguments showing that the QCD strings of SUN cannot flow to these CP1 strings. There will be some other mechanism for them. But okay, I don't want to enter in these details. And okay, there are a lot of future directions coming from this work, at least something that is natural to me. Of course, it would be very nice to have a better understanding of the connection to the actual QCD strings of a joint QCD, but at the moment we cannot make further claim. And also, it would be interesting to break explicitly the remaining U1 of the bulk, for example, putting a mass to the pions. In this case, we will gap the theory and we recover effective string theory in the far infrared. However, since we have this symmetry breaking pattern in the bulk, I think we can also use this model to make prediction on the bound states of these strings, even in the gap theory. And with this, okay, I'll thank you for your attention, and that's it.
Yeah, okay. Thank you for the great talk, Giovanni. And
Thank you.
we can have questions.
Yeah, of course.